Okay, this is the vehicle routing recording. So first click on this MTZ CVRP. Okay, so in the vehicle routing problem, um, we'll have multiple vehicles or maybe multiple trips from a depot. So think of this as like in the middle, we have this depot node. Think of it as like an Amazon fulfillment center or a FedEx depot where they keep all of their trucks or something like that. And from this depot, the loaded truck will leave and drop off all of the packages and then come back to the depot. And so maybe at the same time, some other vehicles going out and dropping off a whole bunch of packages and coming back. Or maybe the one vehicle goes out, delivers packages, comes back, loads up again, goes back out, delivers the packages and comes back, and so on. So I'll just suppose that these number of out and back trips is just equal to the number of vehicles. So let me import network X. We're going to set our number of vehicles to be 4, just like in this picture. And then also, like before, I'm going to have 20 nodes. But these will actually be demand points. So we're going to have a depot, which is going to be node 0 in our case. It's going to be right here in the middle. And then we're going to have 20 other demand points, which I guess in this picture, there's 16 demand points, but we're going to have 20. Okay. So our depot is going to be node 0, and then we're going to have these demand points, which will number going from 1, 2, 3, 4, all the way to 20. Actually, we're going to have 21 nodes in our graph, 1 for the depot and 20 for the demand nodes. Okay, we can create our complete graph on n+1 nodes. And it's going to be a directed graph. So I'm going to do nx dot diagraph here. Okay. And the reason we're using a directed graph, I guess one key reason is that we're going to be imposing constraints just like the Miller-Tucker-Zemlin constraints that we'll be using for the capacities of these vehicles. So we're going to suppose that the vehicle can only carry so many things on it during its trip. Okay. So I can run that cell. And again, we're going to place all of these demand points at random. So all 20 demand points, we're going to place them at random in this unit square. But the depot, we're going to locate that in the middle, just for convenience. It'll look nicer in the picture. So the position of the depot, which is node 0, maybe I should say this is depot. It's going to be 0.5, 0.5, so right in the middle. Okay, so I can draw that. There's my instance, and presumably maybe this one right here is that depot node. Okay, then we'll get the Euclidean distances between all of these pairs of nodes and store that as an edge attribute. Okay, so now we get to set some of this other instance data. So this is the capacitated vehicle routing problem. So we have these vehicle capacities, and it's, I'm just going to say it's 100 units. Whatever the units are there, I'm just going to say it's 100. And I'm going to suppose that all of these other demand points each request 20 units of demand. So I'm going to have a dictionary here that's going to map a node or a demand point I to its demand of 20. Okay, and so Yeah, let's see, we have 20 demand points, and each one of them asks for 20 in demand. So the total demanded is what, 400? And I have 4 vehicles, each with capacity of 100. So all of the vehicles will ultimately be at their capacity in a feasible solution. Okay, so I'll import Gurobi. And first we'll create kind of a relaxation of this vehicle routing problem. This is kind of the easy part. So we'll create our model object. And we're also going to create really the same edge variables from before. So we have a variable for each one of these directed edges. They're all going to be binary variables. The objective in the exact same way. So if you wanted to, you could copy paste this from a previous code. That would do fine. I'll type it out. So we sum all of these variables multiplied by length of that edge. The objective is to minimize the sum of the length of the tours. We'll require that each demand point is entered once. Compose like this. Would sum some xj variables, and it should equal 1. It should be true for all j in the set of demand points. So I'm not requiring this constraint for the depot. Actually, the depot, we will leave the depot 4 times and we'll kind of enter the depot 4 times. So it's only the demand points that we require to enter once. Okay, so this will be summed over the predecessors of j, so the kind of the in neighbors. And we'll have the same sort of constraints about leaving each of those demand points. If each demand point once, this will be xij, this will be j in successors, out neighbors I, and this will be for all demand points I. Okay, so those are the constraints that act on the demand points. But I also need a constraint for the depot. So leave the depot k times. So that's for the number of vehicles. One constraint, and it should, the right-hand side is k, the number of routes or number of vehicles that we're building. So for this, I'm going to sum those xj variables, but sorry, xij variables, but specifically we're pointing out of the depot, which is node 0. So we'll sum this over all successors of the depot. Okay. So I can optimize this. This is just a relaxation, but let's see. I didn't spell this right. Oh. Okay. All right. So it solves pretty quickly. We can get the solution. Our picks are all edges E for E and G dot edges if the X variable is at least 0.5. I can draw it. And I'll use again the same node positions as before. Okay. So you can see here, I guess each node, each of the non-depot nodes has one edge in and one edge out. And then the depot, which is right here in the center, has 4 edges that point out. And it's a consequence of these other constraints that will also have 4 edges that point in. Okay, so this is obviously not a solution that we would be able to implement. And so we need something to, I guess, one, impose that we're getting actual tours that kind of leave the depot and then come back to the depot. We can't have these kind of isolated subtours. And then we also need to impose the capacity constraints on the vehicles. So right now there's no such capacity constraint being enforced. Okay. So the way we can do this is very similar to the MTZ variables or constraints from before. So we'll add these U variables, the node, and of the depot is, it should be equal to 0 in all of these tours. So I can set the lower bound of this variable equal to 0. And I can also set the upper bound of this variable equal to 0. Wanted to, you could also add a constraint like this. You could say this in a position of depot in the tour equals 0. That would be equivalent to what I just wrote. Okay. Each of the other demand points, other nodes, I'll set a lower bound and an upper bound on them as well. And it's going to be equal to, the lower bound will be equal to the demand. The upper bound I can set to the capacity of the vehicle. Okay, so these U variables are no longer really going to be capturing the position of the node. They're going to be capturing how much capacity has been used up to and including that point in the tour. So when you start off, maybe I should go back up here. Okay, so suppose that each one of these nodes had a demand of 1. So when you leave the depot, you've so far visited kind of a total demand of 0. So that's why the kind of the U variable for the depot is 0. Once you reach this first node, let's say it had demand of 1, then you would have consumed or required your vehicle to be carrying 1 unit of demand in order to get to here. Then when it goes to that second node, its U value should be 2 because it's the second node. It's essentially the cumulative demand to get to that point is now 2. And so, yeah, so this node right here, right before it goes back to the depot, its U value would be equal to 4. Let's say in the original MTZ model. And then here, if each of these demands were 1, then this U variable should equal 4. But if the demands at each of these nodes were, let's say, 20, like I said in this problem, the U variable for this node would be 20. For this one, it would be 40. This one would be 60, and this one would be 80. And let's say if the capacity were 80, then that would have kind of met that capacity. So that would have been okay. So that's what the U variables are now going to represent. It's kind of like what's the cumulative demand up until and including that point in that vehicle's tour. Okay, so that is going to lead to some slightly different constraints from before, but they're actually not too different. So we'll add a constraint for every edge, and it's also going to compare the U values for kind of adjacent nodes in a vehicle's tour. So basically, I'm going to write the idea first here. So if edge ij is part of the tour, then the uj value should be at least the UI variable plus demand of j. So however much demand had been needed to get to node I on this tour, plus j, the next node in that route or that tour. Okay, so that's what the constraint is going to enforce. So it'll look like this. Again, we don't impose this constraint for edges that point back to the depot. It's actually this, I should probably say depot. Okay, so what the constraint says is that when you do pick this edge, ij, then yeah, let's see what happens then. So if xij equals 1, this reduces to the ui minus uj plus q is at most q minus qj. We're simplifying this. We can cancel out the q's and then maybe rearrange this. So I put the uj on the other side. And then I move the qj to the other side. So that's exactly what I wanted. I wanted uj to be at least ui plus qj. Meanwhile, if xij equals 0, if I don't pick the edge, I want this constraint to essentially become redundant. So let's double check that. So this would go away. And then I guess this these u values should be somewhere between qi, or between little q and big Q. And so kind of in the worst possible case, this one would be q. The largest this could be would be q, and then the smallest this could be would be qj. So when x is 0, this constraint becomes redundant and really does nothing. So I think those constraints, and then I can optimize. And to be honest, this model is much harder to solve. So I would not be surprised if this takes maybe a minute or longer to solve. So let me go ahead and start typing what we need to visualize this solution. So as you can see, it's making progress, but it's kind of slow. So I think one difficulty with this model is essentially these kind of big M type constraints. So that value of Q is 100, which is 5 times the number of nodes in this graph. And so these big M terms where you have this large number multiplied by a binary variable, these are known to lead to weak LP relaxations, which is why this bound is progressing so slowly. Okay, so finally it solves. It took almost 2 minutes. Let's visualize it. Okay, and so we had essentially 20 demand points that needed to be evenly split across 4 vehicles. So each vehicle should service 5 points. And you'll see here that each one of these little tours does service 5 points. But maybe you can see that these tours kind of overlap with each other. The picture isn't super nice, and maybe that's one reason why it took as long to solve as it did, is that there was really just not a great solution for this problem, for this particular random instance that I generated. Maybe if I generate a new instance, rerun everything here, maybe this new instance will admit a better solution. Maybe it'll solve more quickly and give a better picture. It's still taking a while to solve. Let me try one more time. New random instance. Still somewhat slow. I'll say this is not the state of the art model or approach for solving VRPs. I think it's much more likely that if you're trying to get the fastest possible results for this problem, you would use something called branch and price, as opposed to this is branch and bound, or Gurobi's implementing something like branch and cut. But there's something called branch and price, which is a different kind of large scale optimization technique that's more suited for solving vehicle routing problems. All right, I'll try it one more time and see if it'll solve in 10 seconds or less. Okay, this looks more promising. Yeah, the picture's still not great, but anyway, so you can use this model if you wanted to. If you had more than 20 points, I could see why you wouldn't want to use this if it's taking a whole minute to run, because it depends on how frequently that you need to solve this routing problem. If you were, let's say you're Amazon and you're trying to figure out which packages to put on which trucks to send out to distribute them, you may apply a different procedure than what I've done here. You might use a heuristic, or you might do a kind of a two-step process. In the first step, you may try to group the demand points into clusters. And then once you've kind of grouped these, let's say partitioned these demand points into 4 clusters that are kind of cohesive and compact, then you could essentially solve a TSP instance across each one of these individual clusters. Okay, that does it for VRP.